Dear viewers, today we are going to discuss about the asymmetric synthesis, introduction to the asymmetric synthesis. This topic is taken from the BSc 5th semester chemistry, and this topic explains about the importance of the asymmetric synthesis and the definition of the asymmetric synthesis and the types of the asymmetric synthesis. So, basically what is an asymmetric synthesis? Generally, the asymmetric synthesis is the creation of a or the formation of a unequal proportion of the products in a chemical reaction is called the asymmetric synthesis. Generally, in the stereochemistry, if you take in the chemistry, the stereochemistry plays very important role, where the stereochemistry explains about the spatial arrangement of the atom in the particular molecule here. That means, in the 3D nature, generally we are able to see the molecule in 2D nature here, right. So, in the x and y direction you can see the molecule, but when a particular atom is located in another axis like x, y and z, in that case we are unable to see the third axis, that is a z axis on the blackboard here. So, to explain this phenomena, we will take the help of the stereochemistry. So, your stereochemistry explains about the spatial arrangement of the atoms in a particular molecule. Spatial arrangement means the alignment of the atoms or the orientation of the atoms in a space. So, for example, here if we see the molecule, right, like here this is the molecule. So, where you can see the molecule, this is if you see in the 2D nature, you can able to see the only this and this atoms here, and you cannot see the means outside atom and this particular here, right. So, if that particular molecule is oriented in the 3D form, then you can able to watch the all the atoms attached to particular central carbon atom here. Okay. So, this explains the stereochemistry. And what is the importance of the stereochemistry in a chemistry? So, stereochemistry generally it is very important because where it produces the isomers here. And what are the isomers? So, isomers means where the molecules having the same molecular formula, but they will differ in their properties here. These are called the isomers, and in the isomers we are aware about the isomers like enantiomers are there, diastereomers are there, and structural isomers are there, stereoisomers are there. So, in the structural isomers we have various types like positional isomers and constitutional isomers and chain isomers, and so these are the isomers where you can see the difference in the arrangement of the particular atoms. And in the stereoisomers you can see the enantiomers and the diastereomers, where these in these particular types of isomers where the atoms are means there are mirror images to each other here. Okay. So, means the basis for this particular asymmetric synthesis is the stereochemistry, and the aim of this asymmetric synthesis is for the creation of a chiral center in the substrate molecule or in the product here, where the creation of the chiral center, that means you know that the chiral center means where the central carbon atom is attached with the 4 different groups is called the chiral center here. So, in the asymmetric synthesis where the creation of the chiral center is takes place by reacting with a specific reagent here. Now, we will see in this particular example, here the propionic acid is taken, where this propionic acid where it is having the here the acid COOH acid group here, and below you can see the methyl group here, and in the central carbon where the 2 hydrogens are attached here. So you can see the central carbon atom is not having the 4 different groups here. So you cannot say it is a chiral carbon here. You cannot say it is a chiral carbon because we have only the 3 different groups, but to say the chiral center we need the 4 different groups here. Atoms are the groups here, but we can see only 3 different groups here. That's why this particular substrate is not called the chiral carbon here. Now we are going to create a chiral center by reacting with a specific reagent here. So when we are treating with some specific reagent to this particular propionic acid, so where this propionic acid is converting into D-lactic acid and L-lactic acid here, right. So where here you can see the acid group here. So here this particular D and L both are the 2 isomers here. You can say these 2 are the enantiomer and these 2 are unequal amount of the products. You can see the unequal amount of the product. That means for example, if the D-lactic acid it may be the 90% and the L-lactic acid it may be the 10%, or D-lactic acid it may be the 80% here and L-lactic acid it may be the 20% or 30 and 40 whatever, right. So the aim is the formed products must be with unequal ratio, then only we can say the asymmetric synthesis. For example, if we get the D-lactic acid and lactic acid with equal proportion, that means 50% of D-lactic acid and 50% of L-lactic acid. So 1:1 ratio. If you get the 1:1 ratio, then we cannot say it is a asymmetric synthesis here. Okay. So here for example, if it is forms with the unequal proportion, unequal ratio, unequal amount, then only we can say the asymmetric synthesis here. And to know about the asymmetric synthesis, first of all we must familiar with the terminology involved in the asymmetric synthesis. So the terminology involved in the asymmetric synthesis is first we will see the homomorphic ligands here. So homomorphic ligands means homo in the sense same, okay. Homomorphic ligands, that means the atoms in the isolated form, if they are same, then we can say it is a homomorphic ligands here, right. For example, you can see in this particular model you can observe, right. So here this particular compound say it is the central, this is the carbon atom where it is attached with the 4 groups here, okay. You can take it, these are the hydrogens or chlorines or phenyl groups or methyls, anything you can take, but all are in the same, right, same nature here. If it is hydrogen, this is also hydrogen, this is also hydrogen, this is also hydrogen. 4 different 4 same kind of atoms attached to this particular carbon here. Then we called this is the homomorphic ligands, okay. So all are same here, okay, all are same. In case if we take, okay, if you take the another model, like you can see in this particular model you can see where these 2 are the same and these 2 are the different here, right. So these you can say these are the chlorines, or you can take bromine here, and these 2 are the hydrogens. So you can see the different atoms in this particular carbon. So this is called the heterotopic ligands here, and this is called the homotopic ligands, right. So you can convert the homotopic to heterotopic and heterotopic to homotopic by following some criteria here. So that is the you can create the homotopic to heterotopic and heterotopic to homotopic by substitution method and by symmetry criteria. You can convert the homomorphic ligands into the hetero and other things here, right. So here homotopic ligands, we can see with the example here how to convert this particular homotopic ligands, right, by substitution method, right. So, this is the homomorph compound here, and by substitution of the one of the hydrogen with the different ligand, that is also resulting in the homotopic ligand here, right. For example, so I am going with the replacement of one hydrogen with chlorine here, you can see chlorine, right. So, the replacement of the homotopic hydrogen with chlorine, then what happens here? So, you can see 3 hydrogens are there and 1 chlorine is there, okay. And this is, for example, you say this is H1 hydrogen, this is H2, just you label the hydrogen, then it is easy to recognize which hydrogen is we are going to replace here, okay. So, this is H1 hydrogen, just say, and we got this particular compound, right. And in another operation where we are replacing the H2 hydrogen here, right. So, H2 hydrogen. So, then what happens here? The chlorine comes here. In the earlier the chlorine comes here, and in the next operation where the chlorine comes here. If you see this molecule and the previous molecule, both are same here, okay, both are same. So, we call these are the homotopic ligands here, right. So, the replacement of the one of the hydrogen with the different atom, whether it is chlorine or the bromine or any other atom here, it is resulting in the formation of a same kind of configuration, okay. So, it is called the homotopic ligand here. And another type of the, okay, so another type of terminology involved in this particular asymmetric synthesis is the homotopic phases. This is also one of the important criteria in the asymmetric synthesis, where in the homotopic phase, in the earlier it is homotopic ligand, okay. Homotopic ligand is different from the homotopic phase, where the homotopic ligand where appears in the sp3 carbon, okay, tetrahedral compounds here, and the homotopic phases, it is applicable for the unsaturated compounds here. That means, the carbon must be in the sp2 hybridized state, right. So, for the homotopic ligands, the carbon must be in the sp3 hybridized state here, and for the phases you can see where the carbon must be in the sp2 hybridized state here. Now, you can see with one this example here, okay. So, you can see, for example, you see where this particular compound, just you assume it is a carbonyl, right, the carbonyl compound, right. So, this is the carbonyl compound here, where you can see these two are the some groups, okay, the methyl, right. So, you can say these are the two methyl groups here, and these two are, right. So, these are double bond which are attached with the oxygen, okay. So, just you assume this as a carbonyl compound, that is the acetone, just you assume this as the acetone here, okay. Now, you can see here these two are the atoms, right, attached to this particular carbon, and this is your carbonyl CO group here, right. Now, you can see it is in the planar state, right, it is in the planar state here, it is not a tetrahedral geometry, it is a planar geometry here. Now, you can see when you are reacted with the phenyl magnesium halide, okay, phenyl magnesium halide, that is a nucleophilic Grignard reagent here, right, the phenyl magnesium halide, it is a Grignard reagent. So, when we are treated with the Grignard reagent, then the pH minus, right, the pH minus nucleophile, where it is having the opportunity to attack this particular carbonyl compound either from the top side, okay, it may be attacked from the top side or it may be attacked from the bottom side, that is we call that side is the face, okay. So, it may be attacked from the top phase here and it may be attacked from the bottom, just to assume it is a phenyl group here, right. So, then it may be attacked from the top phase here, it comes from here, this is the favored right. So, favored orientation or means favored direction to attack here, and as well as the bottom face also favored for the attack of the phenyl, because it is in the planar geometry. So, both sides are equal opportunity for the attacking of the phenyl group. Then what happens here? So, when it is phenyl is attacking on this particular carbonyl center, so it is going to produce a compound, right, a compound which is the asymmetric carbon here, asymmetric compound. Okay. And we are getting the, for example, when it is attacking on top side, so we are getting some compound, right, the hydroxy derivative here, and when it is attacking from the bottom side also we are getting the hydroxy derivative, but the stereochemistry different for both the attack here. When it is attack from the top side, for example, if you get the R isomer, when it is attacking from the bottom side we get the S isomer. Then what happens here? Both the R and, right, so both the isomers are homomers here, you can see, right. So, in this example you can see clearly, right. So, when this phenyl group is attacked from this top side here, we are getting this particular product, okay, asymmetric compound, and when it is attacked from the bottom side we are getting this product, okay, bottom phase attack and top phase attack, and both the attack is going to form a homomers. Homomers means same compound here, right. So, upon rotation with 180 degrees here, you get from this compound to this compound. So, both are the same configuration, right. So, these are the homomers and we call the homotopic phases. Homo means same, and where the phase means means whatever the space available to attack that particular carbonyl group here. Now, the heterotopic units, the another type of the terminology involved in the asymmetric synthesis is the heterotopic units, and these heterotopic units are again classified into two types, where structurally heterotopic units and stereo heterotopic units here. And what are the structurally heterotopic units and what are the stereo heterotopic units? So, here the structurally heterotopic units means where this particular substitution of the atom or the group with the third group or the atom here, it results in the formation of a constitutional isomer here, constitutional or the structural isomer. So, we know that structural or the constitutional isomers are different types like positional isomer and functional group isomer and metamers, right, and tautomers. So, these are the structural isomers here. For example, in this particular example, what we are doing, where we are taking this particular propane molecule here, and to this propane where we are replaced one of the hydrogen with the chlorine. We are doing the substitution criteria, right, by substitution criteria, where one of the hydrogen is replaced with the chlorine, then we are getting this particular N propyl chloride, right. So, in the first condition we are substituting the, right, the hydrogen which is attached to the C1 carbon here, and in the next operation or in the next criteria where we are substituting the hydrogen which is attached on the C2 carbon with the chlorine. Then what we are getting here? You can see here we are getting the N propyl chloride. When it is substituted the C1 carbon hydrogen, we are getting the N propyl chloride here, and the substitution of the C2 carbon hydrogen, it is resulting in the formation of the isopropyl chloride. Now, you see where the chlorine is, in the second case the chlorine is on the C2 carbon, and in the first case where the chlorine is on the C1 carbon. Then what happens here? We are getting the different products, right, because the N propyl chloride and the isopropyl chloride both are not same products here, right, because the position of the chlorine is different. Generally, these are the positional isomers, right, these two are the positional isomers, which is the example under this particular structural isomer here. So, we are getting the structural isomers by substitution criteria in the structural heterotopic units here. Now, the stereotopic units, stereoheterotopic units here. So, in the stereoheterotopic units, where creation of the asymmetric center by substitution method. Okay. Now, you see again we are taking this particular propionic acid. Okay. So, we are taking the propionic acid and we are labeled the, in the propionic acid we are labeled 2 hydrogens at C2 carbon, 2 hydrogens as HA and HB here. Okay. Now, we are applying this particular substitution criteria to convert this particular propionic acid into that particular asymmetric product here, right. So, first we are going with the substitution of the HA with the chlorine, okay, HA with the chlorine. Then what we are getting, the configuration is R 2 chloropropionic acid here. Okay. So, what we are getting, R 2 chloropropionic acid, and same thing again in the second method where we are replacing the HB with chlorine. Okay. In the second case we are replacing the HB with chlorine. Then what happens here, we are getting S configuration. Previously we are getting R configuration and after we are getting the S configuration. So, here the R and S both are the enantiomers here, right, and here we are getting the stereoisomers. Okay. So, in the structural heterotopic ligands we are getting the structural isomers here, and in this case we are getting the stereoisomers. Okay. So, this is called the where the replacement of the hydrogens with the chlorine, it is resulting in the formation of the enantiomers. That is why we call this the enantiotopic, right, enantiotopic heterotopic ligands. And the another category is enantiotopic phases. Okay, enantiotopic phases. Okay, where this particular enantiotopic ligands involves in the, right, creation of a asymmetric center to the sp3 carbon, and in the enantiotopic phases creation of a asymmetric center to the sp2 carbon here. Okay, where in the enantiotopic phases where the sp2 carbon is involving in the reaction and we are getting the enantiomer product here, right. So, same example we are taken where this particular okay. So, here this is the, it is ethanaldehyde, right. So, ethanol where we are taking the ethanol here where this particular phenyl magnesium halide is attacking on this particular carbonyl center here, and it is and the attacking is takes place by 2 ways. In the first case where it is taking place attacking from the top side here, and it is going to form the R configuration phenyl ethanol, and in the next case where the phenyl group is attacking from the back side or the bottom side here, and it is resulting in the formation of the S2 phenyl ethanol product here. Now, you can see both R2 phenyl ethanol and S2 phenyl ethanol both are different. So, these are the enantiomers obtained by attacking of the phenyl magnesium bromide, and this particular phenomena is takes place through the phase. So, we called it as a enantiotopic phases here. Now, the diastereotopic ligands and diastereotopic phases. So, here also same criteria is followed, but only thing is where the formation of the products are diastereomers. We know that the definition of the diastereomers where the isomers which are non-mirror images, non-superimposable isomers are called the diastereomers. Okay. So, non-superimposable mirror images are called the enantiomers, and non-superimposable and non-mirror images isomers are called the diastereomers. So, we are getting the diastereomers by when we are following the substitution of the hydrogen with the chlorine. So, you see in this particular olefinic product compound where the labeled hydrogens are replaced with the chlorine. So, we are getting the cis 1 chloro propane here. And in the second case, where this hydrogen is replaced with the chlorine and it is resulting in the formation of the trans 1 chloropropane here. So, we are getting the two different diastereomers here. So, we called it is the diastereomeric ligands, and here the diastereomeric phases. In the diastereomeric phases, where we are getting attacking of the reagent from the two opportunities like top phase and the bottom phase, and the obtained products are the different here diastereomers, right, where this particular tertiary butyl cyclohexanone, when it is treated with the lithium aluminum hydride. So, where when it is attacking from the top side, top phase attack results in the formation of the equatorial hydroxy derivative, and the bottom phase attack is resulting in the formation of the axial, right. So, axial hydroxy derivative here. So, and both these two are the diastereomers. So, we call these are the diastereotopic phases here, and this is the classification of the homomorphic units which is given in this particular flow chart. So, what we have discussed, all these things are summarized in this particular table here. And the prochirality, right, here the prochirality nothing but where the creation of the chiral center in a achiral center, this is called the prochirality here. In this particular propionic acid, where this central carbon is not a chiral thing, because to have the chirality, to exhibit the chirality, the carbon must be having the 4 different group, must be attached with the 4 different group here, but we can not see the 4 different groups here, right. You can see acid group here, methyl group and 2 hydrogens. So, 2 hydrogens are same. So, this is not a chiral center here. Now, what we are trying here, we are trying creating the chiral center by chemical reactions or by biochemical reactions here, right. In this way, we are getting the D lactic acid and L lactic acid here, right. So, where this prochiral center, pro means before the chiral center, means it is not a chiral center, but it can be converted into chiral center here, okay, by means of the chemical reactions or the biochemical reactions. Okay. So, we are converting this achiral center into chiral center. This phenomenon is called the prochirality. And in this prochirality, the nomenclature or the designation is given by two names here. One is Pro R and Pro S. So, what is Pro R and what is Pro S here? Pro R means, for example, here already we have the 3 priorities here. You can see OH, right, hydroxy group and methyl group here, and 2 hydrogens are same, right. So, it is a prochiral center here, and when we are trying to convert this prochiral into chiral center, okay, so you can substitute these homotopic ligands with the third element, that is any other element, different element here, then it may be convert as a R isomer or the S isomer, right. So, that is called the for example, if it is converted into R isomer, it is called the Pro R. If it is converted into S isomer, then it is called Pro S here, right. So, you can say, for example, here HA, when it is substituted with the third different group like chlorine here, then it is going to convert as a R isomer, right. Otherwise, if you substitute this HB with the chlorine, then it may convert into means S isomer. So, this conversion of the R isomer and S isomer is depends on the incoming group here. Okay. So, this phenomena is called the prochirality, and in this prochirality also rephase and side phase. This is also the attacking of the reagent from the either top side or the bottom side, and it is creating the chiral center. And the stereoselective reactions. So, generally the stereoselective reactions are classified into different types like substrate stereoselectivity and product stereoselectivity. Here the substrate stereoselectivity, again 2 types, like that is substrate enantioselectivity and substrate diastereoselectivity. So, substrate enantioselectivity means where when we are having the 2 isomeric substrate here, then the reagent selectively reacts with the one isomer, then it is called the substrate enhancer selectivity, right. Here for example, here in this particular here is a ammonium tartarate when it is treated with the penicillium glaucum. So, this particular penicillium glaucum it is consumes the plus isomer, right, and we will get the minus isomer as pure form here, right. So, one isomer is consumed by this particular penicillium glaucum here, right. So, this is the selectivity, you can see the selectivity in this particular reaction. So, this is called the substrate enhancer selectivity and substrate diastereo selectivity, where here also when the two diastereomers are available, in that case if the reagent is selectively selects the one diastereomer, then it is called the diastereo selectivity here, right. So, in this particular Z estophenone oxime, where it is giving the N methyl benzamide and E isomer, here Z isomer gives a N methyl benzamide and E isomer it is giving the acetonilide, where the proton, right, this reagent is more reactive with this particular E isomer than Z isomer. So, we get the acetonilide as a major product. So, this is called the substrate diastereo selectivity and product diastereo selectivity, where the reagents selectivity means formation of the product, right, it depends on the formation of the product here. So, these are the specificity in the selectivity of the compound. Yeah. So, till now we discussed about the asymmetric synthesis, and here the asymmetric synthesis means where formation of the unequal products in the reaction is called the asymmetric synthesis, and in the asymmetric synthesis so many terminologies are involved, that is the prochirality and pro-R and pro-S nomenclature and homotopic ligands, heterotopic ligands. These are the key key terminology involved in the asymmetric synthesis, and in the asymmetric synthesis we have the different stereoselective reactions, that is product stereoselective and reagents stereoselective here, product stereoselective and substrate stereoselective reactions. And in the substrate stereoselective reactions we have enantio substrate stereoselective and diastereo selective reactions here.